Thank you. Thanks for the introduction again, and welcome back. And if you forgot about the first lecture, then that's fine, because today is a little bit different story. And the first lecture, I focused more on the introduction and some basic constructions about the suspension space. So let me just remark something. So I decided that for the Lyapunov exponent and the coarse exponents that I mentioned at the end of the last talk, I put more detailed theorem and some exercises in the exercise problem sheet. So please check. In there, you can find some detailed statement and relative exercises. And suspension space, last time I think I forgot, I confused with the inverse, but this is the right one. And then you can check that this is a suspension. And if you see the exercise, actually, the suspension is related to the return cocycle I mentioned in the exercise. But the return cocycle is basically the lattice cocycle in the Romance talk. But I think I have a different convention. I did not use the G inverse x gamma. I want to use the Gx gamma inverse. So that's the one thing I want to mention before starting the lecture. OK, so now you can forget everything except the suspension. And the Lyapunov and coarse exponents, we will come back here on the third lecture. But today we will be on the homogeneous world. So there will be no Lyapunov or coarse exponents. So I think the number 3, section 3, is about the leafwise measures. So now I want to introduce what
suspension. Do you mean GH gamma inverse?
So suspension here?
No, the line. GH gamma inverse.
GH gamma. Yeah. Yeah, that was a typo in the first lecture. So the leafwise measure. So I want to start with some probability or calculus in undergraduate course. So I have a tutorial, or R2 if you want, or square in the R2. Then now if I have, in T2, I have a nice measure, which is dx dy, right? Let's say this is x-axis and this is y-axis. I have a dx dy, which is the living measure on here. And if I just divided my torus into 2 pieces, which is half and half, then I think you can say the mu is mu of, this is a partition. So let's say partition is P, is given by these 2 pieces. Then now I can say that this is half of mu of P at 1 plus, let's say, mu of P2, where you can basically, let's say mu is the living measure. You can basically think about the measure on here in restrict to here and here, which is somehow the conditional measure. If you remember the conditional expectation into finite partition, then basically mu 1p is given by mu of A is given by mu of A, mu of the, let's say, box is P1 and P2. P1 and mu of P1 intersection is A. Right? This is how you disintegrate the measure into 2 pieces. You break your measure into 2 pieces corresponding the partitions, with these partitions. Right? I think this is easy. Let's go to a little bit more. This is I think this one is not even in the, this is not complicated. But now let's go to the first year undergraduate course, which is calculus. Now I'm thinking about the partition into the vertical lines. And now my measure mu is, let's say this is partition P, and my measure is dx dy. So what's the Fubini theorem really says? Fubini theorem really says that if you integrate by the mu, then this is f dx dy, and double integration. And then now I can think about it as integration of integration. This is dy first and dx. Right? So if you have this partition, then I want to think about the measure, the conditional measure on this vertical line. So I want to think about mu x comma y. This is the base point. And I want to think about the partition given by the vertical lines. And then now I want to say that this is basically dy. Does this make sense? So I can break down my measure into, for each point, of course, your measure will be same for your measure, this measure lives in the, so your measure lives in your base point with the partition. Your measure lives in this vertical line. If you choose a different point on A, B, then your another measure, another part of the measure will be on this vertical line, right? But they are all dy, but we can identify it. But I want to write down the atom of the partition, that contains base point x, y. I can restrict my measure in the atom, right? And then you can recover the measure d mu by, I want to say that f of the, OK, let's do not go there. You can recover mu from the measure on each atom, right? You can integrate. First, if you want to integrate the function on the tori, I want to integrate along the vertical, which is the atom of the partition first, and then integrate along the transversal, right? This is the Fubini. So now, what I want to do is that if every foliation looks like this, then foliation is basically the space of the foliation is given by the leaves, right? And then if you have a foliation, then you have a natural partition into leaves. The atom of the partition given by the foliation is the leaf. Unfortunately, in dynamics, dynamically defined foliations are not good like this. So typically, what you will see is that I will see the irrational flow. So this is the irrational flow. Let's say given by phi t, with slope, the slope of this flow is irrational number. And then now I have a partition which is given by the orbit. So these are the one atom. And if you choose all the point in T2, then this will be the partition, right? The space of the orbit will give you the partition. Unfortunately, I cannot do the Fubini here, because the reason I don't want to go further, but the reason here is that the space of orbit, the space of the vertical lines are very nice. If you think about the whole space of the vertical lines, then this is Hausdorff space. This is very, very nice. But here, actually, if you think about the space of the orbit, then it is even not, what is it? It is not Hausdorff. So the right keyword is that this is not measurable partition, which I will not define. And the Fubini kind of argument only works when you have a very nice partition, which is called the measurable partition. So I want to give you some keywords that you can find later in the literature. But the main problem here is that it is not measurable partition, so I cannot do that. So what I want to do is instead, even though the space of the orbit is very bad, if you focus on the small box, if you focus on the small box, then your foliation is very, very nice, right? If you only focus on the yellow box, then your foliation is given by the horizontal or vertical lines like this, right? So now what I want to do is that actually, what's the point of this kind of disintegration, this kind of decomposing the measure? I want to think about the measure on the local part. I want to think about the local part of the measure, which is the measure supported on the atom. So here, dy is supported on the vertical line. And here, the mu p1 will support it on the one atom in the partition. So I want to think about the measure mu, and then I want to restrict my measure into the atom, which is the orbit, right? But then now, OK, globally, I cannot do that. However, if you see the small box, then this is fine. And then now, naturally, you can think about the smaller box, but thinner box, right? And then do the over and over again. So if you think about the first box, then this is some thick box. But now maybe you can think about the longer or thinner box. Then it is still very nice foliation in this box. And maybe you can hope that you can patch together. Of course, you should pay something. That's the way of defining the leafwise measure, you will not get the finite measure. You will get the infinite measure. Okay? So this is the intuition of the leafwise measure. And now let's do some math. So now H is the Lie group, let's say. This is more general, but I don't want to go general case. H is a Lie group. And now I want to think about H action on X, continuous action, and where X is the locally compact second countable metric space. And the action alpha is continuous and locally free. That means that there exists open neighborhood of identity in H such that the action map is injective for all X. So now I have like this kind of condition, this kind of setting. Then now I want to say that there is, so now let me just, there exists mu measurable family of locally finite measures nu, because I do not write down mu, I will write down nu first. I will explain a little bit more on H, such that first, if you have a zero measure set in X, I will explain what this object really. But let me just say that, and X is in tori, mu almost every X in X. So for almost every X, I have a measure on H. For every null set, I have for almost every X a null X H of, OK, I think I want to introduce the notation first here. So what kind of object I want to see? So here, I said that I want to break down my measure into each orbit, right? Each leaf. But then now, as I said before, even though the space of orbit is very bad, at least each leaf is well parameterized by the group. So now what I have here is that I have X, and I have a H of X. And now I have a natural orbit map from H to here. And then now, actually, I want to think about this is large X, and measure is in here. And then now I want to think about the measure on here, the orbit. But measure on orbit is sort of not good to think about right now, because there is a better way to think about this. I want to break down my measure into orbit. So my measure, the part of the measure should be if you think about the measure along this orbit, then it is the measure on large X, but I can pull back my measure into H, right? So that's the reason I will say something like this. I have a measure on E, which is a zero measure. Then if you think about the part of this, then you should also get the zero measure. So this is saying that generic point should be generic point on the leaf. Yes?
I'm sorry, just where is mu? What is?
So mu is mu is any probability measure on X. Sorry, yeah. I don't ask that mu is H invariant. Any probability measure, you can get this kind of sequence. And second, I want to see that. So this is the normalization condition. Nu X H of Bohr of radius 1 center that the identity is 1. So here, if you think about the measure restricted to this box, and then disintegrated, or using the Fubini, actually there are lots of freedom to choose the box, right? That's the first thing. But also there is another freedom. I have some finite measure. Maybe let's say this box has measure 1/3. Let's say this box has measure 1/3. Maybe I want to say that this length is this. I want to say that this has measure 1/6, and this has measure 2. And maybe I can get the 1/12 on here, and then maybe I can have a 4 on here. So in dx dy, actually there is another way to disintegrate it. This is 2 times dx times half of dy, right? So there's no canonical canonical normalization. So if I do this kind of box and then disintegrate on here first, and then disintegrate on here, and then patch together, then I need some normalization condition, and this is the normalization condition. Yes?
So what is phi x? Is it the orbit map?
Phi x is the orbit map. Yeah.
So that's alpha then? Alpha restrict?
Yeah. This is alpha restrict to there. Yeah. So yeah, phi of x h is alpha of h of x. Yeah. Thank you. And of course, what I want to do is that because this measure, this sequence of the measure should see the action first. So third, what I want to do is that so there exists full measure set such that if x and h dot alpha of h of x is inside the lambda for h in h, for every x and alpha of h on x, so now I have x on here and alpha of h of x on here, then let's think about I already succeeded to make this. I have a notion of measure along the orbit, and then let's say this is the distribution of measure along h dot x, whatever this means. If there is such a notion, then I have a 2 orbit map from h to h, right? But now if you see the orbit map, that identity goes to the base point. So what does this mean is that if you see this, then let's throw the density. Density is like this, and x is in here. Then along the phi of x, you will see that identity has a peak, right? But on the other hand, if you pull back by the map based at the alpha h of x, then what you see is that I have identity here, and then the peak is here, right? So this is basically saying that, but this is given by the translation, right? If you composite this, then this is basically the translation. So now we have nu x h is proportional to the, nu alpha of h of x is proportional to the RH minus inverse star nu of x h, where RH inverse is the map to h, where the g goes to gh inverse. This is exactly what picture says, right? You have the same measure on the x itself, but if you pull back to h, then because of the difference in the base point, you will see the difference by the translation. And finally, you should be able to recover mu from these pieces, right? So now I want to say that on small enough box, small, nice box, like that, your measure restrict to these boxes, box B, restrict to the box, then this is integration of mu, let's say phi of x star nu of xh, restrict to this box, and then some other measure, some transverse measure. I will not write down very carefully because I don't want to introduce the notion of the nice partition. But basically, yeah, whatever this equation really says, I want to say that if you restrict to your measure on this small box, then your measure restrict to on this small leaf should be integrate to the entire measure on here. So if this is too complicated, and you can see that mu can be recovered by the sequence of the measure. And of course, these are somehow quite abstract nonsense. So basically, there is a way to disintegrate your measure into some bad foliation or bad orbit space. But here's the key point. So theorem or proposition is that this is the important proposition. If mu is H invariant, if and only if mu almost every x, nu of xh is a Haar measure on H up to proportional, up to constant. So I did not mention what is the proportional really means. So here, mu1 and mu2 are proportional if and only if mu1 is basically constant times mu2 for some positive number. So this says that there is no natural Haar measure because Haar measure is infinite measure on the group. You can multiply the constant always. But up to that constant, your measure is Haar measure. If and only if your measure is H invariant. Yes?
Are those measures always full support on H?
Can you say again?
Are those measures you always have full support
No.
on H?
If you think about the Dirac delta mass, then your family of the measure is just Dirac delta mass. So yeah, that's a good point. Nu xh is somehow measurable stuff. So I cannot say anything about the regularity at all right now. But if your measure is H invariant, then I can say that your measure is Haar, so it is very nice regular measure on H.
What's the explicit definition of mu measurable family?
Mu measurable family is that I will write down, but the mu measurable family is the measure. So let's write down. So x to the radon measure, so or projective radon measure, projective measure of H, and then this is the measurable. This is the measurable map. There is a nice reasonable topology here, and then yeah. So yeah, let's erase this because yeah, this is too technical. But now, H invariant implies if and only if it is. So this is the way to detect the H invariancy. And second, now I want to assume that f is x comma mu to x comma mu, and f preserve mu. Mu is f invariant. And assume that f of alpha of h of x is same as let's say phi of h of alpha of f of x, where for some phi from h to h. So now what does this mean? So I have a h orbit on here, and I have f of x and h orbit of f of x, right? But then now, what does this mean is that if you go to the h, and this is phi of x, phi of f of x, then basically this really means that the dynamics, this is the dynamics on x, right? So I don't know what happens on here. This is just arbitrary measurable map. But there is a nice parameterization so that if you go to the parameterization, then your dynamics is given by just automorphism, right? Then your measure, because your measure is f invariant, so your measure should see somehow f. That means actually, because there is a lot of left and right things, so now I want to say that nu of x, so let's say nu of f of x at h, because your measure is invariant under h, so your density on here is same as density on here. And if you go back to h, then this really says that proportional to phi of h star nu of xh, nu almost every x. So your measures are on here, right? And in here, dynamics is very bad. I don't know what is f. But if you go back to the parameterization, I know the dynamics exactly, right? So you will get you will see there from the F invariancy. OK, but these are some abstract sense. So now I will go to the very specific setting. Which is the suspension.
By the way,
Yeah.
in the proportionality that you mentioned at the proposition, like how do we quantify little h?
What do you mean to quantify little h?
Like how does that h like depend on say like x, for instance?
No.
So for any h, for any mu almost every x, we have the proportionality.
OK, yes, but let's do not go there because h is usually uncountable group. So yeah, but let's say for h, mu almost every x. For each h, mu almost every x.
Okay,
let's do that. Let's do that first. Yeah.
That's good.
But yeah. OK, it does not go up very well. But I think the first one is the most important thing. So I will not show you the second proposition. But now let's go to our example. SL3R, and gamma is a lattice. And now I want to think about the continuous section on compact metric space. And then now I have a suspension. And let's say mu is the probability measure on x to the alpha. So this is our setting. Any probability measure on here. And now what I want to do is the following. So this is basically argument by Katok-Spatcher. Now I will show you that how you can use the higher rank and why suspension is useful. So now let's took the beta inside in the root. So for instance, I want to think about let's say A first. A is our diagonal group. And my beta is given by A is T1 minus T2, where this is A. So this is the root. And then now I want to think about the U beta is the root group. So here is the example. Example here, U beta should be 1, 1, 1. What is it? 1, 1, 1, 1, 2. So this is star. And then now I want to think about the element in the corner. That is, in this example, A should be e to the t, e to the t, e to the negative 2t. The corner means that A and U beta commutes. OK? And this is higher rank phenomena. You cannot find this kind of element at all in the SL2R. So now what I want to do. What I want to do is that in this setting, actually you can see some, again, nu xh, nu x, I want to think about the nu x. So now let's write down the assumption first. Assume that mu is alpha tilde, which is the g action on the suspension. Assume that mu is alpha tilde of a invariant ergodic. So now I know that my measure is invariant under the diagonal group. And this is very easy to find because large A is amenable. But now I want to claim that because of the higher rank phenomena, nu of x u beta is homogeneous. More precisely, nu of xh is either atomic, either delta E or her on U beta, which is just the Lebesgue measure in the one-dimensional real line. Because your U beta is basically R, right? Your U beta is basically one-dimensional, one-parameter group, one-parameter subgroup. So your measure in U beta should be either Dirac delta mass on here, or it is very nice measure on U beta. This is a priori very surprising, because your measure is very, I choose an arbitrary measure that is invariant on ergodic under alpha tilde of A, but now I can cook up the homogeneous structure on the leaf for this measure. The point is homogeneous for me. OK, how can you do that? So now what I want to do is that because A is inside the corner of beta, that means A and U beta commute. And what does this mean in the actions? So I have x. This is U beta of x. And this is A of x, U beta of A of x. And then now if I go back to my parameterization, and this is identity and this is identity, the commutativity really means that this is just identity. And if you remember the second part, what does this mean? This means that nu of A of x U beta is proportional to the nu of x and U beta. Right? But now I have a normalization. I think I erased it. But now I have a normalization that the Borel of radius 1 in U beta is 1. And also I have Borel of radius 1 in U beta is also to 1. That means actually this is not proportional. This is exactly the same. Right? Proportional means that there is a constant, that this is constant times this. But on the Borel same set, this has the same measure, so you should have the same measure. But now let's go back to here. Alpha tilde A invariant ergodic. Ah, sorry. I need to assume the plus some assumption. Sorry. This is quite weird, not weird, but this is quite annoying assumption, but this is really needed. So now I want to introduce one assumption, which is that assume that this is a big assumption though. Alpha tilde of A is ergodic. Then nu of x U beta is same as nu of A dot x, which is alpha tilde of A of x. U beta means that this is measurable family, but invariant under the A. So nu x U beta is constant mu almost every x. This is the ergodicity of the alpha tilde A. If you have a function that is invariant under the dynamics, then you should be constant. OK, then what do I have? Now, I want to say that because on the other hand, if you think about the change of the base point, which is given by the translation on A, oh, sorry, yes, it's constant. So especially for U in U, where so let's say this way. So if x and U of x are well defined on the full measure set for, yes, let's say this, for mu almost every x. Let's say this way. And U in U beta. So here I lied a little bit because the leafwise measure is only defined almost every point. So maybe here your measure is not defined. So here I really assume that if you have generic point x, and if your u dot x is also generic, then you have the same thing. So what do I have here is that I have a x and u beta dot x. And if your measure is not supported only on the point, and maybe this is in the support. So let's say this point is in the support of the nu x u beta, then I can come back by ergodicity. So that this is u dot x, so that I can have, they are same. So you should be careful about almost every point. But if you believe that this is constant, then this should be same for every u. But now what I want to have? I want to write down that this is actually, if you remember the third point in the proposition, this is proportional to the nu the right translation. Let's say because this is one-dimensional, which is abelian. So now I just write down u inverse, but this is just translation star of nu of x u beta. And then now this is same as nu of x u beta. So what does really mean here is that I have a density like this, but this should be same as like this, right? So if you have a peak like this, then you cannot get this. You cannot get this property, because your measure, basically, what does this mean? Your measure u beta is invariant under translation, right? So this cannot be happen. And what is the definition of the Haar measure? What is the defining property of the Haar measure? Haar measure is that actually it is invariant under the all translations, right? And now we have almost there, right? Because up to proportionality, we have that. Invariant up to proportionality. Your nu of x u beta is same as the after translation, but up to proportional. And actually, there is an exercise that because in this case, you have a one-dimensional subgroup, you can actually find all possible Radon measure on the real line that is invariant, that has some nice set of u that says that your measure is proportional up to some translations. It should be something like constant times to the exponential e to the alpha t dt. So please do the exercise. After here, actually what we can do is that maybe you cannot come back. Maybe there is no support on the u beta. Maybe there is no point you can come back. Maybe there is only, this is the only point your measure supported. Then you should come back here. And that's exactly this case. If you have other supports, then actually you can come back here, so you have an additional invariancy. So if your support is not discrete, then actually you can get the entire Haar. So this is actually in the exercise. So do some more careful calculus. Doing some more careful calculus, you can actually show that this is atomic or Haar. So please check the exercise. And the right statement is the following. So this is what I cheat a little bit. So I have a nilpotent Lie group. And this is the isometric assumption, which I used on here, right? I only know the proportionality, but this is identity is isometry. So using the isometricity, basically, this is also identity on the parameterization, but isometry assumption, there is a dynamics, additional dynamics, which preserve the mu. And if your isometric dynamics on leaf is ergodic, then actually, please see the exercise. I defined what it is. This is a subgroup of H. There is some subgroup of H that acts transitively on the support, but let's just ignore this. Additionally, if you have a contracting dynamics, then your measure coincides with the Haar measure on a connected Lie subgroup. So let me give you the example on there. So in the example, small a is isometric, right? But there is an element in A. There is an element A prime inside an A that A prime contracts U beta. I cannot cook up the, no, I think I can cook up the element. For instance, e to the t, e to the negative t1 or something like that, or negative t and t. So there is an element inside in the A that contracts the leaf. So this is again higher rank phenomena. So basically in the higher rank group case, usually you have isometric dynamics and contracting dynamics simultaneously. And then what does this really mean? So let's just forget about something like this. If you have a higher rank group that satisfies something, then what will you get here is that your measure, nu xh. So let's just focus on the last sentence. Let's say h is two-dimensional. So h is like this. A priori, your nu xh is just some measurable stuff on here. I don't know how it looks like. However, using the higher rank, these are really higher rank property. Using the higher rank, what can I do is that either this will be maybe point, or maybe even line. Your measure should be at the line. If your h is R2. Your measure is either point, or there is a closed, if you think about the closed Lie subgroup in R2, then that's either connected, trivial, R, or entire thing. So this is the way to get the additional invariancy and regularity. So a priori, this is just measurable set. But at the end, using the higher rank, you have a very smooth object on here. Make sense? So let's see. So now what I want to do is that so any questions so far? So the idea is very simple. I think I presented it very complicatedly, but basically, what's the idea is that if you have isometric dynamics, then something like, let's say here and here are support. X and Y, P and Q are two support in the measure. Then isometricity will preserve isometricity, and ergodicity will come back to Q. And then now if you go back to because F is isometry, your measure at here is same as measure at here. But then you can go from P to Q by the translation. So this means that because F preserve the mu, your measure at this point is same as measure at this point, but their difference is given by the translation. So your measure is invariant under the translation. And Haar measure is given by defined by invariant under the translation.
Yes? How do you get rid of this possibility of this exponential time constant because of this?
That's a good question.
Is it the contraction thing?
That's the contraction thing. Actually, if you have exponential things, then either you can call Lapierre or Lapierre-Young. They know the density very precisely in the one-dimensional case. So you can just kill out directly. Or if you have a contracting, your curvature of the exponential density should be blow up. That's the exercise, actually. Your curvature of this exponential the density should be blow up. But now, because your dynamics preserve the probability measure, we have a Poincare recurrence. So there is a positive measure that your density cannot blow up. So yeah, that's the exercise. Any other questions?
Why is the support always connected?
That's another good question. So let's just assume that they are not connected. But then now what can you do? So let's say here. Let's say I know that there are two pieces of the homogeneous guy. Using again the contracting dynamics, I can contract these two over and over again. So at the end, you should have only one. That's the idea. And I think I put this on the exercise, some similar question on, or not. But yeah, basically contracting dynamics really make the connectivity. Does this make sense? So yeah, if you have a two piece of the two connected component, then using the contracting dynamics G over and over again, then this connected component has distance goes to 0. And then measurable object is continuous on the large set of the measure, and then your distance should be at least 0, actually 0. That's the idea. Any other questions? OK, I think I'm very slow, but I planned to give a proof of the normal subgroup theorem today, but at least I can start. So because these are some abstract settings, so now I want to show you how this can be applied to the classical theorem. So theorem by Margulis normal subgroup theorem. Let's say gamma in G SL3R, lattice, and then N is the normal subgroup, and then either N is finite or index is finite. And I think already Roman told how this proof goes. So the strategy is that the proof is that show that gamma mod N has amenable property if N is infinite, and also gamma mod has property T, because gamma has property T in this case, then done. Right? Amenable with property T should be finite. And now this one you already learned from the Roman's mini course, so I want to focus on here. So how can you show the amenability? Actually, Margulis really showed the following: measurable factor theorem. And I stated the theorem in the exercise more carefully. So let me say this. So let's say P is upper triangular subgroup. And now let's say gamma acting on x comma mu x. This is a measure space, measurable space. And assume that there exists if there exists gamma equivariant factor map from x to, let's say, psi and psi star m g mod p. So this is that your action is measurable factor of gamma action on here by left translation, and the measure you get is just the push forward measure on here, and m g mod p is the Lebesgue measure on g mod p. G mod p is the space of full flag, so you can think about the Lebesgue measure on there. The space of full flag is nice space, the more or less manifold. So you have a Lebesgue measure. Then x with the psi star m g mod p is gamma equivariantly measurably isomorphic to g mod q with, again, this is nice space, so you have a Lebesgue measure. So you can classify all measurable factor, or measurable gamma factor of g mod p. And an exercise is that the exercise for you in the exercise problem list is that the measurable factor theorem implies that gamma mod n is amenable if n is infinite or n is non-central. So this one I gave also a hint in the exercise list, so please try. So basically, I want to show you how can you prove the measurable factor theorem using this argument. but there's no measure. But let's see. This is the measure, but if you think about the exercise again, there is no gamma invariant measure on here. So this is just somehow Lebesgue measure on G mod P. But then how can you cook up the measure, mu, on here? So here's the statement. I think I want to at least give you how can you cook up the measure we want to study. So now I have pi from G mod P to X. Did I say psi? Sorry. I want to coincide the notation with the exercise list. So let's say pi. So pi.
Oh, by the way, could you remind us what is Q?
Oh, Q, sorry. Yes. Q here is that for some Q contains P. Yeah. Yeah, parabolic subgroups. So now this will give the lifting map from here, right? G maps. If you have a measurable factor, this is gamma equivariant. Then you have a the lifting map, which is that G goes to what? Pi of, this is small pi, this is big pi. Pi of GP. This is the lifting map. And then now I want to make that X is same as G mod Q. So what I want to do? I want to think about the stabilizer, basically. Let's say Q is defined by Q in G such that the large pi of GQ is same as large pi of G for, let's just ignore the almost every right now, but let's write down at least for the MG almost every G. So these are the measurable maps, so I need to care about the hard measure almost everywhere. So, but let's just ignore this if you don't want. But why can you see that why do I want to think about this? Because I want to say that X is same as G mod Q, right? At the end, measurably. But then now, how can you cook up the G mod Q? I want to say that everything that is saying, if you multiply by some element in the right, then it's the same, then this will give you what? This will give you pi bar from the candidate of the measurable map, which is gamma equivariant. Make sense? The gamma action is on the left. So now, if you think about the gamma equivariant map, this is gamma equivariant, left gamma equivariant. And then now if I multiply by right, so I can quotient by right, and then still this is the left gamma equivariant. And this is just measurable. So what's the problem? I already got the measurable map from G mod Q to X. So I have a map from here to here. Then what's the problem? The problem is that I don't know that this is injective. Right? Maybe it is something like, it can be more collapsed, very weird way. Not about the translation. Maybe this, we don't know that this is injective, but now actually we enough to show that pi bar is injective almost everywhere. Make sense? Because my measure will be the push forward measure. So surjectivity is basically in here. But now if I want to show that this is measurable isomorphism, then I need to show the injectivity. Then now, let's see, how can you show that A map is injective? Well, the one way I know is that draw the graph. So let's draw the graph. Let's say this is the psi. I think I use the psi for my notation. And then this is just G goes to G comma pi of G of X. And then the measure I want to think about is that this is a hard measure on here. And then I want to think about the push forward measure on here. So if you don't want to track the measure, then that's fine, because this is somehow almost in there. But let's see, I want to think about the measure on here and here. And then I think I put the exercise on the list. That will give you the G action on G times X on G times X. Let's say this is, I think this is mu tilde in my notation in the exercise list. Mu tilde and mu tilde, this is nice probability space. Not probability. This is measurable space with infinite measure mu tilde. But now I want to go to the quotient out by gamma. And then now I have measure mu. And because this pi is gamma equivariant, and actually you can quotient it. The explicit calculation is for you. You can do that. You can write down what is the function here, map from here to here, and then this is well defined because pi is gamma equivariant. And then from here to here, actually you can go to quotient measure, which is mu. That is the probability measure. So these are all exercises for you. These construction. But basically what I do, I have G on here, and I have X on here. And then now I know that I want to draw the graph which is psi. But I already know that psi is not injective along the Q. So there is a direction. So let's say G, and this is GQ. Along the direction, this is not. So this is pi of G, and this is G. This is the point on the graph, and I know that this is not injective along the Q orbit. But now, actually, injectivity of the pi bar is given by that. Let's write down here. In this picture, what do I want to show? I want to show that pi bar is injective. That means that I don't want to have other point on here, which is the image of the graph, right? So does this make sense? So I want to show that pi bar is injective. That means I want to, if I draw the graph, then I don't want to see the point outside of each level. I don't want to see the point outside of the Q orbit, right? OK, so I think I'm almost at the time, but let me just give you the idea, because I think I start at 2:33. So let me use the 5 more minutes. So what I want to do actually here, so measurably, I don't want to see the point outside of the Q orbit. And what does this really mean is that, okay, but before that, how can you see the other point, how can you see the point other than Q orbit? Actually, if you write down the V as the subgroup, so let's say this way. So for simplicity, let's say assume that Q is the parabolic subgroup. We already know that Q is parabolic subgroup, which is the closed subgroup contains P, but except this is the closed subgroup contains P, and here. And then now let V is the missing roots. If you think about the V, then actually G is more or less Q times V locally, right? You have a Q and V, and then you can make the IE for every G. Actually, G in G, G can be written as Q, G and H. You can go from G to H by just H, Q, V, Q prime. And what does this mean in the picture? In the picture, if I see the other point H on here, if I see the other point in the graph, then now I want to go to Q first, and then V is transversal to here, and then now I want to go to the HQ. So if you see the H in the graph, if you see the point, this point h in the graph, then because pi is invariant under the right Q translation, if your h is inside in your graph, if this point is inside in your graph, then this whole line, which is HQ orbit, should be in the graph. And then now what I want to see here is that, okay, I can go from here to here, and now this means that your measure mu is basically the graph, right? So your graph sees this line and this line. But now, if you think about the transversal, then almost every point are generic on here. Almost point are generic on here because your measure is basically Haar measure on here, on the G. You push for the Haar measure. So your measure is Haar measure on the base. So basically your measure in the graph is Haar along here and Haar along here. And if you think about the transversal V, then you should be able to see the two generic points. So there exist x and y, where y is v times x in the graph are generic and mu generic. So these are in the mu almost every point. So what does it mean? So I have a full measure set and I have a full measure set. And if you think about the transversal, these are very nice foliation. Especially if you think about, there are many ways to go there. But if you think about the map from here to here by translating by v, this is actually bi-ellipsis. And bi-ellipsis maps the full measure set goes to full measure set. That's the key point here. So if you have a full measure set here, then if you think about your friends, your intersection with the Q line on here, your full measure set goes to full measure set. So there is at least one friends. There is one pair such that they are in the generic points. Because this movement is bi-ellipsis map. And bi-ellipsis map maps the Haar measure to Haar measure, Haar almost every point to Haar almost every point. And actually what does this mean is that mu x v is non-atomic. And basically, in this case, we are done. Let me spend one more minute because sorry for I don't want to eliminate the coffee break, but let me use the one more minute. So there is so basically the support of the measure mu x v, which is the leafwise measure, will not be atomic. However, one exercise for you was that in the list is that mu x v is non-atomic. Will give you the fact that mu x u21 or mu x u31 are non-atomic. So there are sort of the product structure. So if you know that your measure is non-atomic on here, then your measure should be non-atomic on here or here. But then now, can you connect with the measure rigidity scheme I mentioned here? Let's just assume that this is non-atomic. Then what's the other possibility? Which is Haar. So if this is non-atomic, then this is Haar. And do you remember the one proposition which says that Haar, if and only if, mu is u21 invariant. But now, of course, there is one thing you should check. There are lots of exercises, not lots of. There are a few exercises you need to check because I want to say that mu is ergodic along the one parameter subgroup in A. A priori, we don't know. But the exercise for you was that first, the stabilizer of mu in G is actually Q. And second, as a measurable space, this is, let's say, this is x of alpha. As a Q space, x alpha with mu is isomorphic to G mod gamma, comma, Haar measure on G mod gamma. And here, if you have a Q action, this is ergodic. And using the mathematical phenomena, every one parameter subgroup is every non-compact one parameter subgroup is ergodic. So there is no obstruction to apply. And then you can see the contradiction. Mu is u21 invariant, but u21 is not in Q. But I also says that stabilizer is only Q. So you cannot get the additional invariancy. And that's it. Then that means that I cannot get the two generic points in the same V orbit. And that means that, what does it mean? This is coming from the if phi bar is non-injective. Then there is a pair such that along the V orbit, there is a pair. They are in the generic points. But that means that in fancy language, this means that your leafwise measure is not atomic along the V orbit. But then now you can get the additional invariancy, and this gives you the contradiction. So I show this, and then this will give you the measurable isomorphism as a gamma space. OK, so I think I was too fast. I know that, but sorry about that. If you have any question, I'm very happy to answer. And then many details I put as an exercise. So please check. And I also mentioned this. This approach is given by Aaron, Federico, and Jiran. So for more general case and the more details you can find in their article. So thank you. Yes?
So I was getting confused by this, so I imagine other people must be too. You say the measure is non-atomic when you find 2 points in the support of the measure. Yeah. Why is 2 points enough to make it non-atomic?
So, OK, I should be a little bit more careful because the right way to say is that, so if actually the right way to say this is that the opposite, the contrapositive. If mu x v is atomic, then it is injective. That's much easier to see. Because you cannot, along this line, they are all singleton. So you cannot see other points on here because we really foliate the entire G.
Oh, and it's the contracting dynamic.
Yeah.
If you're atomic,
yeah, exactly. If you are atomic, then you should be really the singleton. Using the contracting dynamics. So yeah, actually, you can do my exercise. That's the right way to show. The right way is that actually, if this is atomic, then this is injective. Using the contracting dynamics, if it is atomic, then it is singleton. So yeah. Yes.
I mean, kind of similar, I guess. You said before that to show that the support is connected, you need to use Lucent's theorem, and then isn't it just Poincare recurrence again? At least in dimension 1, I think
Thank you. You're right. I think Poincare recurrence is enough. Yeah.
This composition of measures that you mentioned at the beginning, is it true for locally compact?
Sorry, can you say again?
That is composition of measures that you mentioned at the beginning of the action of your Lie group. Is it true also for locally compact?
Instead of the just probability measure?
Instead of Lie group.
So actually, the general setting is the general setting in this direction I know is given by Einsiedler and Lindenstrauss. H is locally compact second countable topological group, metrizable, I think, and then acting on locally compact second countable metric space. Maybe you can remove one or two assumptions, but
I think in the way you described it, you also need unimodular, but they have a new construction where you don't need unimodular and it's in the full.
Yes. They also don't need the unimodular. The reason I actually put the Lie group and nilpotent Lie group on here somewhere is that actually if you have a contracting dynamics, as I wrote down there, then your Lie group should be nilpotent. If you have a contracting automorphism on Lie group, then Lie group should be nilpotent. And that's actually, the unipotent is our main concern. So unipotent is nilpotent. So there's a contracting automorphism.
Last question? Thank you.
Thank you.